Hi folks! The following is our first video on alkenes. I'll be talking about addition reactions to alkenes and the thermodynamics of these, as well as the hydrohalogenation reaction of alkenes. A class of reactions that we'll be talking about for alkenes are known as addition reactions. Imagine starting with your alkene and adding an X and Y group across the pi bond of it. In this so-called addition product, you've lost the pi bond of the alkene, you have a new carbon X bond, and a new carbon Y bond. To explain alkene reactivity, we need to consider the pi bond of the alkene. The carbons of the alkene themselves are sp2 hybridized, so they are trigonal planar. The double bond of the alkene is a pi bond that's made up of side-on overlap of two unhybridized p orbitals. This pi bond has electron density both above and below the plane of the alkene. And this electron density can be used in reactions. One way in which an alkene can react is that it can behave as a base. For this proton transfer, I could draw two curved arrows. One from the pi bond of the alkene to the hydrogen of the acid, then from the middle of the HA bond to A. In this proton transfer, you would form a new carbon-hydrogen bond to one of the carbons that was previously a part of your alkene. And notice that the other carbon that was formerly a part of the alkene now has 3 bonds instead of 4, so it has a positive charge. My other product of the proton transfer is the conjugate base, A-. In addition to alkenes serving as bases, they can also serve as nucleophiles. The pi bond is the nucleophilic site of the alkene, and you could imagine it behaving as a nucleophile to attack an electrophile. Here I'm just writing a general electrophile E+. This nucleophilic attack would have one curved arrow from the middle of the pi bond to the electrophile E. In your product, you would have a new bond between one of the carbons of the alkene and E, and the other carbon has lost its 4th bond and is therefore now a carbocation. I now want to talk about alkene addition as well as elimination, which we've seen previously. So addition would be adding 2 groups across the double bond of the alkene to make a product. If I started with HX, my addition product would have a new carbon-hydrogen bond and a new carbon X bond. In contrast, elimination would look like starting out with our substituted product. We've previously seen alkyl halides for this, where X is a halide, and elimination is the loss of H and X and formation of a pi bond to create an alkene. We'll want to consider the thermodynamics of the forward reaction, addition, and the reverse reaction, elimination. Recall that the Gibbs free energy is equal to delta H minus T delta S. And let's consider a particular example where we're looking at the following tetrasubstituted alkene and adding HCl to it. We could calculate the change in enthalpy for this reaction by looking at the sum of the bond dissociation energies for the bonds broken minus the sum of the bond dissociation energies of the bonds formed. In this reaction, I am breaking a carbon-carbon pi bond and an HCl bond. I've given the bond dissociation energies here. And I'm forming a carbon-hydrogen bond and a carbon-chlorine bond. Plugging in these bond dissociation energies to my change in enthalpy calculation, I get negative 33 kilojoules per mole for this reaction. Because delta H is negative, I would call this addition reaction exothermic. Now let's consider our entropy term. For the addition reaction, I'm starting out with two molecules, the alkene and HCl, and I'm making one single product. Because I'm decreasing the number of molecules, the change in entropy would be negative. So let's consider our negative enthalpy and negative entropy terms in Gibbs free energy. The delta H term out front would be negative, and entropy itself is negative, and there's a negative sign in front of the T delta S term. Taking the negative in front times the negative entropy term would give a positive value for the whole negative T delta S term. So you could think about this negative for enthalpy being in competition with the positive for entropy. And recall that we want delta G to be negative overall for our reaction to be spontaneous and favorable. So let's consider we have a low temperature. When this is the case, the T term will be small, and the positive thing is going to be smaller than the negative one. Delta G will therefore be negative, and this would mean that the addition reaction is favorable. When you go to higher temperature, this minus T delta S term starts to dominate, making delta G positive at really high temperatures. Having delta G greater than 0 is unfavorable, so we would expect that this reaction would not proceed to give the addition product at high temperatures, and would instead favor the reactants, the alkene and the HCl. So going back to our original diagram up at the top, the addition reaction, going from an alkene and something else to the addition product, is going to be favored at low temperatures, whereas the reverse reaction, going from your substituted alkyl halide back to an alkene and HX, will be favored if you go to really high temperatures. The first reaction that I will discuss for alkenes is known as hydrohalogenation. Hydrohalogenation means an addition of hydrogen and a halide across the double bond of the alkene. So imagine starting with an alkene. I'm showing a particular example of a di-substituted alkene, and adding HBr to this. This reaction would form two products. In both reactions, I've added H to one carbon of the alkene and Br to the other carbon of the alkene, and the only difference in my products is the stereochemistry. In the products, the carbon that is attached to bromine in each case is a chiral center, and I've formed two enantiomers of product. I want to walk you through the mechanism of this hydrohalogenation reaction. It's going to begin with a proton transfer. The alkene will act as the base, and HBr will act as the acid. I will have two curved arrows, one from the middle of the alkene to the hydrogen, then from the middle of the HBr bond to bromine. This reaction would form a new carbon-hydrogen bond between one of the carbons of the alkene and the hydrogen. In this case, you don't have to worry if the hydrogen would add to the right or the left carbon. And the other carbon of the alkene now has 3 bonds and a positive charge. And in this step, I've also formed the bromide conjugate base. The carbocation is a strong electrophile, and bromide can serve as a nucleophile. I'll have a nucleophilic attack, taking a lone pair from bromine and forming a bond to the carbocation. This step forms the carbon-bromine bond in the products. To understand the stereochemistry of this reaction, we have to go back to thinking about the carbocation intermediate. The carbocation is sp2 hybridized and planar. The nucleophilic attack, where you form the new bond between bromine and the carbocation, could occur with the bromide coming in from above the carbocation, in which case a wedged bond to bromine would be present in the product, or the bromide nucleophile could attack the carbocation from below the plane of the carbocation, in which case the carbon-bromine bond would be drawn as a dash instead. We would expect that equal amounts of these two stereoisomers would form, and in this case, it would be a racemic mixture, because I've formed two enantiomers here. I want to show you how I would draw the reaction coordinate diagram for the previous hydrohalogenation reaction example. I start out with my alkene and HBr, and my intermediate is a carbocation with a bromide anion. I have one barrier between the starting material and this carbocation intermediate. From this carbocation intermediate, there's a nucleophilic attack step to form the carbon-bromine bond. So there's a second barrier corresponding to the second step of my reaction. So there are a few things I want to note about how I've drawn my barriers and the energies in my diagram. I drew the products as lower in energy than the starting materials to indicate that this reaction is favorable as long as the temperatures are fairly low. I placed the carbocation intermediate higher in energy than the starting material because the carbocation is unstable due to its incomplete octet, and unstable molecules will appear higher on the reaction coordinate diagram. And last, I drew the biggest barrier for the reaction as the first step, going from the neutral starting material to the carbocation intermediate. I would call this highest barrier my rate determining step. I now want to talk about the regiochemistry for hydrohalogenation of an alkene. Which constitutional isomer of product would be formed? Things get more interesting and complicated when you have different substitution of your two carbons of the alkene. So notice this carbon on the left has two carbon substituents, whereas the carbon on the right of the alkene has a carbon substituent and a hydrogen. Now we want to imagine adding HBr to this alkene. We can form three potential products. One where you add bromine to the left carbon and hydrogen to the right carbon. Then we also have to consider what if we had added hydrogen to the left and bromine to the right. This other product also has that same hydrogen on the left, bromine on the right pattern, but I've drawn these two as separate products because the carbon with the new bond to bromine is chiral in each case. What's observed is that the major product is the one where bromine has added to the carbon with two methyl substituents on it, and hydrogen has added to the carbon with one methyl substituent on it. Organic chemists refer to this major product, where the halide has added to the more substituted carbon of the alkene, as the Markovnikov product. And the product where the halide has added to the less substituted carbon is known as the anti-Markovnikov product. This is named after the discoverer of this regioselectivity, whose last name was Markovnikov. What we observe experimentally, and which we need to explain, is that the halide preferentially adds to the more substituted carbon of the alkene, in a Markovnikov manner. So let's consider the first step of this hydrohalogenation, the proton transfer. In this step, you're adding a hydrogen to one of the carbons of the alkene, and if you add hydrogen to the carbon on the right, it forms a tertiary carbocation. Alternatively, if you'd formed the new bond between carbon and hydrogen on the left, you form a secondary carbocation as well. The tertiary carbocation is more stable than the secondary one. So let's consider a reaction coordinate diagram for just the first step of this reaction. My alkene and HBr have complete octets and are relatively low in energy. The carbocation intermediates are both less stable than the starting materials, but they have different stabilities from each other. The tertiary carbocation is more stable than the secondary carbocation, so I've drawn it as slightly lower in energy. And then we have one barrier between the starting material and each of these carbocation intermediates. The higher the energy of the intermediate, the higher the energy of the barrier needed to get there. So notice that the tertiary carbocation is more stable, but it also has a lower barrier going to its formation. Because it has the lower barrier, the tertiary carbocation will form faster. And the major product comes from this more stable carbocation intermediate that is tertiary. So the reason we see more of the product, where bromine has added to the more substituted carbon, is because we preferentially formed a carbocation at that position, and wherever the carbocation was, the bromide nucleophile adds. Alright, so let's consider the following reaction, where I have a tri-substituted alkene being treated with HBr. To predict the product that's formed, we first need to consider what possible carbocation intermediates could this alkene form. I'll start by drawing out the proton transfer leading to the carbocation intermediate. The alkene will act as a base to deprotonate HBr. One possibility is that hydrogen could add to the left carbon of the alkene. That would make this carbocation intermediate. Or what if hydrogen had added to the right carbon of the alkene? In this case, I would form a different carbocation intermediate. So I need to consider which of these would be formed preferentially. In one case, I have a tertiary carbocation, and in the other case, I have a secondary carbocation. The tertiary carbocation is more stable, so that's the intermediate I will form, and I would not form the less stable carbocation intermediate. So to predict my major product, I just need to think about the nucleophilic attack of the tertiary carbocation. Imagine bringing in your bromide nucleophile to this tertiary carbocation center. In the product, I would have a new carbon-bromine bond at this position. So, I've drawn this product first without worrying about stereochemistry, and now I need to identify if I've formed any new chiral centers in this reaction. The carbon with the bromine added to it is a new chiral center. So now I need to worry about what if the bromide had added from above or below my carbocation intermediate. You would want to draw all possible stereoisomers of product. In this case, there are two possibilities. If bromide added from above, one stereoisomer of product would have a bromine wedged bond, and if bromide added from below, you would have a dash bromine bond product as well. In this case, these molecules contain a single chiral center, and they are enantiomers of each other. I would draw both of these enantiomers as my predicted major products for this reaction. Because a carbocation forms in hydrohalogenation, you need to be on the lookout for possible carbocation rearrangements. An example of this will show up in this tert-butyl substituted alkene, which is being treated with HBr. 3 products form, in this case. 2 of the products formed from addition of bromine to the left carbon of the alkene. Those are these 2 products, which are enantiomers of each other. And there's actually a 3rd product as well, where bromine has added further to the left of the molecule. It turns out that this other product is the major one. And notice that in this product, I no longer have a tert-butyl group. One of my carbons has moved to be a methyl group toward the middle of the molecule. This is a sign that rearrangement by a methyl migration has occurred. The mechanism will begin with a proton transfer. I'll use the pi bond from the alkene as the base to deprotonate HBr. I preferentially add the hydrogen to the less substituted carbon of the alkene, so that I form the more substituted carbocation intermediate. In this case, it is a secondary carbocation. This carbocation can rearrange by a methyl shift from a neighboring carbon. I would draw my arrow from the middle of a carbon-methyl bond to the carbocation. After this rearrangement, I have a new carbon-methyl bond at the carbon that was formerly my carbocation, and the carbocation is now tertiary and more stable. Now I need to consider, what if I had nucleophilic attack of the secondary carbocation intermediate, or what if I had nucleophilic attack of the tertiary carbocation intermediate? I would bring in the bromide to my carbocation center. Bringing in the bromide to the secondary carbocation would form two stereoisomers of product. I have a new chiral center at the carbon with the bromine attached to it, and the bromine could be a wedge or a dash. The other possibility is, what if the bromide attacked the tertiary carbocation instead? This would form a different constitutional isomer of product. This product is achiral, so we don't have to worry about drawing stereochemistry. This product, which is the result of carbocation rearrangement, happens to be the major product of this reaction. When trying to predict the products or draw the mechanism for hydrohalogenation reactions, I like to think about 4 considerations. The first consideration is, what is the nucleophile and what is the electrophile in the reaction? For alkene hydrohalogenation, in the first step, the alkene acts as a base, and you're adding the HX as an acid. This forms a carbocation intermediate and a halide anion. In the second step of the mechanism, the carbocation acts as an electrophile and is nucleophilically attacked by the halide nucleophile. The next consideration I like to make is to determine what bonds are being broken and formed in this reaction. Hydrohalogenation breaks a carbon-carbon pi bond and an HX bond, and it forms a new carbon-hydrogen and a new carbon-halogen bond. Next, I consider the regioselectivity of hydrohalogenation. This reaction has Markovnikov selectivity, meaning that the halide adds to the more substituted carbon. And this is the case because this carbon was the more stable possible carbocation intermediate. And last, we need to consider stereochemistry for our reaction. And if you have a new chiral center that is forming, you're going to get both potential stereoisomers of product. The last thing I want to mention about hydrohalogenation is just a little bit more on regioselectivity. So the mechanism and other information I've shown you today have to do with Markovnikov addition, in which the halide, in this case bromide, is adding to the more substituted carbon of the alkene, meaning that hydrogen adds to the less substituted carbon of the alkene. It is also possible to get what's known as anti-Markovnikov addition of HX. Anti-Markovnikov means that the halide added to the less substituted carbon of the alkene, and hydrogen adds to the more substituted carbon of the alkene. What you do to promote this regioselectivity is you add an alkyl peroxide, written out as ROOR, or ROOR. You add this into your reaction. We're going to use this reaction as a useful way to get anti-Markovnikov addition of HBr, but it proceeds by a different mechanism, so I want you to be able to predict the product that would form, but we won't get to the mechanism until later in the course. Alright, so in this video I introduced addition reactions to alkenes. I talked about how addition versus elimination can occur and can be varied based on the temperature of the reaction. Then I talked about our first alkene addition reaction, known as hydrohalogenation, the addition of a hydrogen and a halide across the pi bond of an alkene. I talked about the mechanism, the preference for forming more stable carbocation intermediates, and I talked about reaction stereochemistry. That's it for this video. I will see you in class.